This is an animation of a square-threaded power screw that is used to move a collar along its length. The power screw rotates, and so long as you don't allow the collar to rotate, then the collar will move up or down the screw depending upon which way the screw is rotating. That way you can get this collar to do work. The speed with which we move depends upon the rotational speed of the shaft and the pitch of the threads, and the amount of force we can generate on the collar is influenced by the torque we apply. This is all related to what we're going to talk about bolted connections as well. With bolts, the amount of torque you supply determines the preload in the bolt and the compression of the bolted connection. It's likely not obvious that there's a simple relationship between our understanding of power screws and of bolts and nuts, but there is, and we'll get to it in a short bit. Now, we're interested in bolted fasteners because they are not permanent. There's great value in being able to do field assembly and disassembly. It makes for easier maintenance and replacement of components, and it allows you to adjust the final position of components for final alignment. Now, the basic structure of the nut and the bolt is as shown here. We have the head of the bolt over here to the right. The head is often washer-faced and has a fillet radius to decrease the stress concentration at the head. The entire shank of the bolt could be threaded. If it's not threaded, then we have an unthreaded shank, which is shown in here. The threads are running out on the shank, and that creates a stress concentration factor. So there are problems of stress concentration there and problems up at the head. The nut threads onto the threaded portion of the bolt, and we have to keep in mind that there will be a threaded length and a non-threaded length, and then there's an overall nominal length, all of the things which are specified and are fabricated according to standards. So the basic thread definitions are shown in this slide. The pitch is the distance between two adjacent threads. And if there is only one thread running down the axis of the bolt, then for each turn of the bolt, you advance by amount equal to the pitch. Now, it's given a separate name. It's called the lead. The lead is how far you move forward for each full turn of the bolt or the nut. The other key things in here are the major diameter, which is the diameter of the shank portion of the bolt. You can think of that as the smooth-sided rod which is threaded through some manufacturing process. It is the largest diameter. There is a minor diameter which occurs at the base, the bottom of the threads. That's in there. And then there is the pitch diameter, which is the average between the major and the minor diameters. Now, I said the pitch is equal to the lead if there's only one thread. And so here's an example of 3 different bolts fabricated with 1 thread over here on the left, 2 threads here in the middle, and 3 threads over here on the right. So the pitch is the distance between identical locations on adjacent threads. But if you start to thread from the top, so in this case we start threading in 2 locations along the diameter of the bolt, and because of that, the pitch will be the distance between these 2 adjacent threads, but it is not equal to the lead. The pitch is equal to the lead if the number of threads is 1, so the lead L is going to be equal to the number of threads times the pitch. So if n is equal to 1, the lead is equal to the pitch. If it's equal to 2, the lead is equal to twice the pitch. And if the number of threads is equal to 3, the lead is equal to 3 times the pitch. It is simply how far the bolt will advance for one complete turn of the bolt. Now, all of these bolts are built according to standards, and the American National Thread Standard defines the basic thread geometry. These things are exceedingly important because these standard geometries allow for interchangeability. You don't have to buy all your bolts and nuts from the same manufacturer. So the UNC is the Unified National Coarse Threaded Bolt. It's used for general assembly, frequent disassembly. It's not at all good for vibrational applications, and it is the thread spacing that is normally specified. If a threaded fastener is required for a high vibration environment, you usually use a fine thread, and you can also go to an extra fine series for aircraft and instrumentation. The thing to take note of here is that thread geometries are specified. There are very specific relationships between this median line and the width of the thread at that median line and how that is related to the pitch, which is the distance between identical locations on adjacent threads, and the way they top the threads off to create a land at the top and at the bottom. So that's the key here, just that there's a standard approach to making the thread. Right, this is a table of diameters and areas of metric threads. You'll notice that you specify in the M series, you specify the major diameter, D, in millimeters. So an M14 would be a metric 14 millimeter major diameter bolt. An M14-2 would be a pitch of 2 millimeters between adjacent threads on that M14 bolt that you specified. The tensile stress area is identified as 115 millimeters squared in this case. So we're looking at this one right here, and it has a minor diameter area of 104 square millimeters. The important thing is if you look up here at this tensile stress area, which is specified as 115 square millimeters, is the effective cross-sectional area of an unthreaded bar that has the same strength as the threaded region of this particular fastener. Now, if we specified a fine pitch, that's over here. All of these things in these three columns are fine pitch series. So let's say we had an M20 1.5. So it would be 20 millimeter nominal diameter bolt, the distance between adjacent threads equal to 1.5, and a tensile stress area of 272 millimeters squared. The same thing is true for the diameters and areas of the unified screw threads. The UNC, which are all the coarse threads, that's over here, and then the UNF, which are the fine threads, over here. So a 3/4 10 would be a 3/4 inch nominal diameter. That is the large diameter. 10 threads per inch in the UNC with a tensile stress area of 0.334 square inches. A 3/4 16 would be a UNF series, and it would have an effective cross-sectional area of 0.373 square inches. So that tensile stress area, as I mentioned, is the area of an equivalent unthreaded rod with the same tensile strength as the threaded rod. And we're going to use that when it comes to strength specifications and fatigue specifications for bolted connections. But before we get there, I want to go back to the square and ACME thread, the power screws that we were talking about. They have a very different kind of thread geometry. Square threaded power screws are just what you imagine they would be. They have a pitch which locates identical geometric features on adjacent threads. The top land is P/2, the bottom is P/2, and the thread depth is also P/2. So these sorts of threads, you can see, have a relatively large cross-sectional area, and so when they are loaded, if you get a lot of strength out of that particular type of thread. This is an ACME thread, so if you're loading it this way, you induce a normal force that is going to be a bit larger. So we'll get to that in a moment when we start to calculate what sort of torque is required for a given frictional interface to move a nut along an ACME or a square threaded rod. We started this video off with an animation of a power screw with a nut on it, and this is another example of that. This is a device that takes this worm over here and it meshes with a gear that is fixed so that it can't move. So as the worm rotates, the gear rotates and moves this power screw up or down. And that power screw then can be used to exert a force and lift a load. We're going to imagine power screw is going to be loaded with a force. There's going to be a nut that's moving along the power screw, and the force is equally divided along the sides of that nut. We want to determine how much torque needs to be applied either to the shaft or to the nut in order to advance the power screw against an applied force F. And the way we will do that is we will identify a lead angle lambda, which is the angle of the thread relative to this horizontal that passes through the axis of the shaft. We identify the mean diameter, which is the midpoint of the thread width, and we ask ourselves how much torque is required to raise the load F. The approach that we take is to completely unwrap a thread from around the axis of the power screw. And if we do that, since the diameter is dm, the distance of unwrapping is pi times dm, and that lead angle is lambda, and we know that the force F is acting downwards, and we are trying to push that force. Just think of it this way. You're trying to push that up this inclined plane. So to raise the force, we want to push it up the inclined plane. That force generates a normal, and that normal generates a friction resistance that resists the motion up the plane. And the coefficient of friction is F. If we want to lower the weight, we change the direction of the applied load. We're now going to call it PL for lowering, and we're trying to push this down the plane, this weight that generates this force F, and the friction force opposes that. Now we got to pull out some equations and do a little bit of math. So what we have to do is reproduce these triangles and look at the case for raising the load, which is here. And remember, this is the x-axis. The y direction is here. And we want to take some of the forces in the x, some of the forces in the y. So if you look at all the forces here for raising the weight, we have this PR is positive x direction. We have minus n times the sine of lambda. Lambda would be the angle right in here. So minus n sine lambda, and then we have minus fn cos lambda. In the y direction, we have minus f pointing down. We have minus fn sine lambda, and we have n cosine lambda. For lowering the weights, here's the y direction. Remember, this is the x-axis. We know that in some of the forces in the x direction, we have minus PL, minus n times the sine of lambda, that's going to be that component right there, plus fn times the cosine of lambda, and the sum of the forces in the y direction for lowering the weight are given by this equation. We take those equations and rearrange them and solve for P, and we find that to raise the weight, we get this equation right here, and to lower the weight, we get this equation right here. So that's a force that is required. PR to raise the weight, PL to lower the weight, where the weight is F. Lambda is the lead angle. Little f is the coefficient of friction. Lambda is the lead angle. Those are important things to keep in mind. So now we just rearrange this by noting that the tangent of the angle lambda would be equal to the lead divided by pi dm. That's the complete unwrap of the thread around the axis of the power screw. We plug that into these equations up there, and we get equations E and F for raising and lowering the weights in terms of the force we're trying to apply axially, the lead L, the mean diameter, and the coefficient of friction. In order to determine a torque that must be applied, we are simply taking the force, multiplying it by a distance to the axis, and the distance to the axis would be the mean diameter divided by 2. So we take that force, that's the force to raise it, and includes this term in F. We multiply it by dm over 2, and that gives the raising torque. The lowering torque, we simply multiply dm over 2 by the lowering force, and we get these two equations right here. All of these things fit easily into a spreadsheet, by the way. And so the most interesting result that we get out of this is something called the self-locking condition. So this is the equation for the lowering torque. If the lowering torque is negative, the load will lower itself. Well, this is not something you generally want. When you jack up a car using a scissor jack, you don't want it to just lower itself under the weight of the car. So you want to make sure that the lowering torque is positive. So you have to apply a force to lower it. And under those conditions, the screw would be self-locking. And in order for it to be greater than or equal to 0, this numerator term right here has to be greater than or equal to 0. And that says that pi times the coefficient of friction times the mean diameter has to be larger than the lead distance L. So if you note that L divided by pi dm is tangent of lambda, the self-locking condition says that the coefficient of friction has to be greater than the tangent of lambda. The other thing that's kind of important is torque efficiency needed to raise the load. If there were no friction, we simply let F equal 0 in the raising equation, and the torque with no friction just boils down to this. And so the efficiency of the power screw reduces to a ratio of the friction-free to the friction torque requirement, and you get this equation right here. So it's easy to calculate the efficiency of the particular power screw system that you have developed. If ACME threads are used, they have an angle to them. They're not square. And so we're raising the force using a slightly different net applied normal force on the thread. It's F over cosine alpha. And so the raising torque is a little bit different. It looks like this. The other thing that we have to think about is collar friction. Now, I want to step back for a second because we're going to use power screw results to help us understand torque requirements when we put bolts into bolted members. And so we have to apply a torque to create a preload in the bolt. And for a bolt, the head is going to be creating friction against the washer or the plate that it's clamping. And we're also going to have friction in the threads of the bolt. And so the relations that we derive here for power screws are directly applicable to bolted members. So in this case, we add a collar friction. So we put a collar on this, and that collar is going to be spinning while we're pushing this weight up. And that creates another frictional work. And so all we do is take the force F times the collar friction. That becomes a friction force. We multiply that by the average collar diameter that is engaged with the weight. That's dc over 2, and that becomes a torque that works just against collar friction. It's now time to put some of those equations to work by solving an example problem from the Shigley textbook. That's what we will do in the next video.